This video will be discussing the Millikan Oil Drop experiment. The oil drop experiment was first performed by Robert Millikan in 1909. The experiment is based on electrically charged oil droplets moving in an electric field. In the original experiment, the droplets were ionized using an X-ray beam. Then, by adjusting the electric field and measuring the velocity of the droplets, the charge could be derived. A modern equivalent performed was similar, however a sample of thorium-232 was used instead to ionize the droplets. From the spray bottle, a fine mist of oil droplets were formed which would fall into the space between the plates. Then the thorium isotope is exposed, which ionizes the oil droplets to have a negative charge. By applying a voltage across the two plates, an electric field is formed which causes a force to act on the droplets in the opposite direction of the gravitational force. When setting up the equipment, the spirit level and adjustable feet were used to ensure it was level. Before taking measurements, the plastic spacer needed to be measured and the focusing wire inserted. Then, after refitting the shroud and adjusting the focusing lenses, the wire was brought into focus. After removing the focusing wires, the wires were used to connect to the power supply and the power was switched on. When the droplet is at terminal velocity, the air resistive force is used. This states that the gravitational force is equal to the falling velocity times the friction coefficient. When introducing an electric field to raise the droplet, the following equation is used. This is also shown in the figure and can be used with the air resistive force to rearrange to calculate the charge. This is shown in the combined equation. This equation calculates the charge, Q, from the mass of the droplet, m, the acceleration due to gravity, g, the electric field, E, and the relationship between the rising and falling velocities. The final equation substitutes out the mass of the droplet, instead using the density of the oil and Stokes' law. This gives the following. To collect results, the ionization source was set to the spray position and the oil was sprayed into the chamber. The video shows that the oil droplets entering the chamber are out of focus and will need to be focused before observing. After bringing the droplet into focus, the control lever was switched between a state of reduced charge, causing the droplet to fall, and a state of increased charge, causing the drop to rise. This clip shows the process of calculating the droplet rising velocity. In practice, this was done using a stopwatch. From measuring the time for the droplet to travel a specific distance, the following table was created. This was plugged into the previous equation with the following parameters. Rho was the density of oil given as 886 kilograms per cubic meter. G was the acceleration due to gravity given as 9.81 meters per second squared. D was the distance between the plates and this was measured at 8.4 millimeters. V was the voltage of the power supply set at 500 volts. B is a Stokes' law constant and is given as 0.0082 Pascal meters. P is the atmospheric pressure and was given as 10,000 Pascal. Finally, eta is the viscosity of air and was taken from the figure showing air viscosity at different temperatures. Using this equation with the rising and falling velocities gave the table containing the droplet charge. The apparent charge for each droplet will correspond to an integer number of missing electrons. By calculating the lowest denomination of the droplet charge, it can be used to calculate the charge of a single electron. Using this method, the charge was calculated as 1.32 times 10 to the minus 19 coulombs. This experiment had several different quantifiable errors, the first being the distance measured. As each grid line was 0.1 millimeters, the error for this measurement was plus or minus 0.05 millimeters. The next error was in the time measurement, as the timing process used was non-optimal, and the stopwatch was used to time the droplet's movements. Ideally, the movement should be recorded and observed in playback as shown earlier, as this will give more accurate results. In the experiment, however, a value of plus or minus 0.1 seconds was used. There were also less quantifiable errors which caused the experiment to vary a random amount. This includes the Brownian motion of the particles. This can be seen in the video as the droplets seemingly jiggle, and this is down to the air molecules bumping into them and causing random motion. Finally, there were the vibrations of the equipment, such as someone bumping into the desk, which caused the droplets to jolt in a random direction. This ruined some results and meant that they needed to be repeated. To summarise, the charge of an electron was calculated as 1.32 times 10 to the minus 19 coulombs, which is very close to the known value of 1.6 times 10 to the minus 19 coulombs. The largest error of the experiment was measurement of the time, as this was done by eye and so created an error of plus or minus 0.1 seconds. This could be diminished by recording the eyepiece with a camera and using software to count the exact time between crossing measurement lines.